Greetings everyone. Myself Aleena Thomas from the Department of Mathematics, Indian Institute of Space Science and Technology. Today I'll be presenting our work on the controllability and observability of heterogeneous network systems with distinct node dimensions and inner coupling matrices. This is a joint work with Mr. Abhijith Ajayakumar and Dr. Raju K. George belonging to the same department. In this presentation, I'll brief about standalone systems, their controllability and observability, define what a network system is, formulate our model, and state the main results. A linear system S is specified by three matrices A, B, and C, where A is the state matrix, B is the input matrix, and C is the output matrix. The system is said to be controllable if given any two states x0 and xf. The system could be translated from the initial state x0 to the final state xf in a finite time tf. That calls for the existence of a square integrable control function u, in the sense that the system x dot equal to ax plus bu solves x at 0 equal to x0 and x at tf equal to xf. Further, the system is said to be observable if for any given initial condition x0, there exists a finite time tf such that the knowledge of the input and output on the fixed time interval 0 tf uniquely determines the initial point. Now we are moving on to network systems. In today's complicated world, all the systems that we encounter in daily life are not as simple as a linear system. For example, gene regulatory networks, neural connections in our brain, or power grids, all are networks. So that calls forth a attention to connecting various linear systems to form network systems. Network systems can be broadly classified into two: homogeneous network systems and heterogeneous network systems. A network system is said to be homogeneous if all the nodes follow the same dynamics A, B, and C with the same inner coupling matrix H. Inner coupling matrix is which determines the inner interactions of the nodes of the system. And with the aid of this similarity in node dynamics, the network system could be modeled using Kronecker product, and the system is given by these two equations: x dot equal to phi x plus psi u, which is the state equation, and y equal to cx, which is the output equation. Here phi stands for the matrix identity cross A plus L cross HC, psi stands for the matrix del cross B, and C stands for the matrix identity cross C. Note that L delta is the network topology. Now, how to bring about heterogeneity in this system? Heterogeneity can be brought about by changing one or more or any possible combination of the state, input, output matrices or the node dimensions. Now, n such nodes integrated as a network works as a single standalone system wherein the state matrix is phi, input matrix is xi, and the output matrix is c. And the definitions for controllability and observability carry forward from the standalone case. Now here, we are going to consider a network consisting of n nodes, each having distinct dimensions, and also we have chosen the inner coupling matrices to be different, and these are aligned under a network topology L, and delta is the input matrix. So the individual nodes are governed by these two equations: xi dot equal to ai xi plus summation beta ij hi yj plus del I bi ui, and the output equation yi equal to ci xi. Now since the dynamics are different here, we couldn't employ the Kronecker product, and plugging in this output equation into the first state equation, we'll get the individual node dynamics as xi dot equal to ai xi plus summation beta ij hi cj into xj plus del I bi ui. Now this network system is given in compact form as x dot equal to phi x plus xi u, y is equal to cx, where phi is equal to a plus gamma, where a is the block diagonal matrix consisting of ai's as their blocks, gamma is the matrix beta ij, hi, cj, psi is the block diagonal matrix consisting of del I bi as its blocks, and c is the block diagonal matrix with ci's as the blocks. And a word on the order of these matrices, phi is an n by n matrix where n is the sum of all ni's, where ni is the dimension of ai, and xi is an n by p matrix where p is summation pi. Now moving forward to the main results, we have got one necessary and sufficient condition for network observability and necessary conditions for network controllability. So the first one is the necessary and sufficient condition for network observability. The network system C5 is observable if and only if all the nodes Ci, Ai are observable. Illustrating this with an example, we are considering a system with two nodes C1A1 and C2A2. With the aid of the Kalman's condition, we can see that C1A1 is unobservable and C2A2 is observable. First, let's try to assemble these systems under a chain network with external control input to the second node only. And we can see that this system is unobservable again by using the Kalman's rank condition. Further, if we align these nodes in a cycle topology with external control input to the second node, there also we'll see that the system is unobservable. Or in short, we can say that unobservable nodes could not possibly be aligned to form an observable system. Moving forward to the second result, it is a necessary condition for network controllability. If there is a node with no incoming edge, then for the controllability of the network system, it is necessary that that node is controllable. Furthermore, it is under an external control input. Looking to an example, we are considering a two-node system where both the nodes are having external control inputs and these are aligned in a chain topology. You can see that here V1 has no incoming edge and these are the dynamics. Again, by using Kalman's rank condition, we can see that the network system is controllable. Further, the first node, that is A1 V1, is one with no incoming edge. If we check Kalman's condition for A1 B1, we can find that it is controllable, and already we have defined an external control input. The next result is also a necessary condition on the network controllability. Here we are considering a node with no external control input. Then for the controllability of the network, it's necessary that AI HI is controllable. Looking to an example, we are again considering a system with two nodes with external control input to the first node. Dynamics are given by these matrices. You can see that the network system is controllable. And here the second node does not have an external control input. We can verify that A2H2 is controllable. The last result is a relation between controllability of the system and observability of individual nodes. If the number of nodes is greater than summation rank bi, where I ranges over all those nodes with external control input, and a further condition is added that there are no loops in the topology, then for the network controllability, it is necessary that at least one of the nodes is observable. Moving forward with an example, we are considering a two-node system with external control input to the first node and the nodes are arranged in a cycle topology. These are the node dynamics. We can see that the network system is controllable and the only node having external control input is the first node. Their rank of B1 is 1, which is strictly less than 2. And we can see that the second node is observable, whereas the first node is unobservable. So there exists at least one observable node. So this was our work. We considered a network system wherein heterogeneity as much possible is added. All the nodes are having distinct dimensions. Inner coupling matrices are chosen to be different. Then we could find out a necessary and sufficient condition for observability and necessary conditions for controllability. These are our references. Thank you.